In line with our simulations of multi-pulse diode rectifiers, let's now discuss the 24-pulse diode rectifier in Plecs. Here is the single line diagram of the converter systems. On top of we have the grid, followed by the phase shifting transformer. As we also mentioned before, the phase shifting transformer are quite important for implementing this type of converter systems. Since we have 24 pulse a rectifier system, that means we need to have a phase shift on the secondary side of 15 degrees each secondary. And the number of P6 bridges is 4, which are connected then in series. The whole DC connections then are connected to the load, represented by a resistive part and an inductive part, RD and LD. Now the model in Plecs is just an extension of the previous 18 pulse rectifier. We just added one more secondary side of transformer principally and added another diode rectifier bridge. If we look into the script file to the left, we have the grid voltage of 10 kilovolts, grid frequency 50 Hz. In this case, we considered the converter voltages to be 700 volt RMS line to line. And since we have star and zigzag connection of transformer, the turns ratio are also going to be the winding ratio. So these are actually to write as a turns ratio is equal to winding ratio. And same for read the remaining turns ratios. So we see 1 as 4. 1 is missing here. We just added the fourth secondary voltage here, and let's also add this one, VG divided by S4, and we need to update the values corresponding to the turns ratio or the winding ratio here as well, and save it. I considered, for the simplicity of the consideration, all the same voltages here on the secondary side. And let's see the connection setting parameters. The other parameters, as also like the previous ones, we took as variables and arbitrary values input here. Later we will consider the impedance calculations. This will vary. So it's always a good idea to initialize this type of parameters as variables. And for the first transformer, we have the number of turns as 1, and for stepping down is 1 divided by the turns or winding ratio. If you remember from the single line diagram, we need the phase shifts as following: so minus 15, 0, 15 and 30 degrees. Since it's specifying a lag of secondary, so if we input 15, it will implement that phase shift of minus 15 degrees. Continue similarly with the other 3 transformers here. We have 0 phase shift and winding ratio TR2. For the third one, we have plus 15 degrees. So since it's a lag, if we take minus 15 degrees, it will be a leading phase shift. And the turns ratio or the winding ratio is TR3 as specified, and TR4 here, and a leading phase shift of 30 degrees. The load, I'll disconnect it for the time being to track the no load conditions. Let's save the model. And for simulation, I'll take 5 periods and let's run the simulation. Seems to be complete. Yes. No, it's not. Let's see where the problem then is. It seems we have an error here. It's an unrecognized functional variable VB. That means here is the mistake, line number 14. It should be VG. If we rerun, there seems to be no problem. Let's open the voltage levels first. So we connected the measurement blocks first to the high voltage side of the transformer, and then the remaining 4 secondary sides are connected here. Let's check the values and the phase shifts quickly. So this is the cursors are already placed for 1 period. You see the green curve here. First 4 curves or windows are for the secondary sides of transformer, which were, if you remember, set for 700 volts. See, all first 4 are 700 volts. And the last window is for the high voltage side of the transformer, representing 10 kilovolts. And the corresponding phase shifts are also noticeable. You see here and here, the phase shifts are implemented accordingly, 15, minus 15, minus 30, and so forth. If we see the voltages here, and I would like to take 1 period, let's take a delta and specify 20 milliseconds, and we see our cursors. Let's put it somewhere visible and zoom in that region. If the settings are correct, we should count the number of pulses to be 24. Let's start here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So the idea of multiple pulse, 24 in this case, is working if we have the phase shifting transformers properly set. Again, if we take just 1 pulse, for example, I mean 1 period of the partial DC voltage from here to here, I'm taking the topmost one as the reference. We should calculate, since we have 4 B6 bridges, so 24 divided by, is it so? Let me check. No, this doesn't apply here. So if we consider 20 milliseconds, we should see 24 pulses as we do here. Now let's connect the load and see the effects of current flow. Rerun the simulation. We should see the impact more or less on the grid voltage or the converter voltages. As you see, some parts of the voltages are lost during the commutation. The DC current, so for multiple ripples, the DC current is so almost pure DC with the very little pulsations, and the partial voltages are also affected due to the current flow. But if you see the complete DC voltage, it's almost a pure DC. Now for some application this could be interesting, and if it is required, then this is the way we can implement using Plecs simulation software. Thank you.